star formation takes place. This is a fundamental process in the universe. For example, the Orion Nebula is a region of intense star formation, where gas and dust clouds are collapsing to give birth to new stars. Part of the nebula collapses due to gravity at the start of the process. Heat from the condensing material eventually causes nuclear fusion to ignite in the new star's core. Understanding the life cycle of stars and the evolution of galaxies depends on these areas of star formation. The lifespan and ultimate fate of the stars created in these nebulae, whether they collapse into a white dwarf, burst into a supernova, or form a neutron star or black hole, are determined by their mass. Star formation is intimately linked to the evolution of galaxies. The appearance and evolution of a galaxy are determined by the rate and distribution of star formation within it. For instance, spiral galaxies that are actively forming stars contrast with elliptical galaxies, which have younger star populations and less noticeable star formation activity. Through a variety of processes such as star formation, mergers with other galaxies, and interactions with their surroundings, galaxies undergo evolution. The building blocks of new stars are gas and dust in galaxies. As these resources are depleted or ejected from the galaxy, star formation slows down and the structure and color of the galaxy change. Over the years, the study of these cosmic structures and processes has been spearheaded by a number of astronomers and astrophysicists. Edwin Hubble's classification system for galaxies established the groundwork for comprehending the variety of galaxy forms. Our knowledge of these structures has expanded as a result of later research by astronomers employing ground-based observatories and telescopes like the Hubble Space Telescope. Astronomers such as William Herschel and his sister Caroline Herschel made pioneering observations of star clusters and nebulae in the field of star formation, which helped pave the way for more in-depth research on star-forming regions in the future. With the use of contemporary radio and infrared telescopes, we have been able to look into these hazy, dusty areas and see the star birth processes in astonishing detail. These structures and processes have an astounding scale. While nebulae are smaller, they can still cover several light-years. Spiral galaxies, like the Milky Way, can span over 100,000 light-years across. Over millions to billions of years, the processes of star formation and galactic evolution take place, demonstrating the universe's dynamic and ever-changing nature. The universal principles governing the cosmos are emphasized by the evolutionary connections and structural similarities among various cosmic entities. These processes show a cosmic synergy, from the formation of stars in nebula to the evolution of galaxies, and from the vast spiral arms of galaxies to the complex patterns in nebula. Comprehending these similarities emphasizes the interdependence of all cosmic phenomena and offers insights into the nature of our universe. We are able to observe more and comprehend more theoretically, which helps us to gradually solve the universe's mysteries and uncover the fundamental harmony of the cosmos. Gravity as cosmic glue in galactic clusters. Galactic clusters are some of the biggest structures in the universe, made up of hundreds or thousands of galaxies held together by gravity. Gravity causes galaxies to gravitationally assemble into massive conglomerations that can span millions of light-years, which is how these clusters form. A major feature of galactic clusters is their gravitational pull, which controls how member galaxies move and interact with one another. For example, the Coma Cluster is a massive cluster with over 1,000 identified galaxies, situated approximately 320 million light-years away. Such clusters may undergo galaxy mergers, galaxy shape distortions, or even the creation of substructures within the clusters as a result of gravitational interactions. Another important object in the study of dark matter is the galaxy cluster. The gravitational effects observed in these clusters cannot be explained by the visible matter, dust, gas, and stars. This disparity points to the existence of dark matter, an invisible material that accounts for a sizable portion of the mass of the cluster. The direct result of gravity's influence is observed in galactic clusters as gravitational lensing. This phenomenon happens when light from objects behind the cluster is bent by its strong gravitational field, enhancing and warping the image of those far-off objects. The distribution of dark matter in clusters has been better understood thanks to research on gravitational lensing. Black holes in stars. Nothing can escape from a stellar black hole, a region created when massive stars collapse due to their extreme gravity, not even light. Understanding gravitational extremes has been revolutionized by the study of these objects. A key turning point in this field was the discovery of Cygnus X1, one of the first suspected black holes. Cygnus X1, which is 6,000 light-years away, was discovered thanks to its X-ray emissions, which are the product of matter being drawn into the black hole from a companion star. These systems offer vital insights into the behavior of matter in strong gravitational fields and the physics of accretion. Supermassive black holes are found at the centers of the majority of massive galaxies, if not all of them.